Dear students, myself, Dr.A.Venkatesan, Assistant Professor, Department of Mathematics, St.Joseph College of Arts and Science, Autonomous, Cuddalore. In this video, we are going to learn simply connected domain, multiply connected domain, some theorems related to simply connected domain, and Cauchy integral formula. Now we are going to see the definition of simply connected domain. A simply connected domain D is a domain such that every simple closed contour within it encloses only the points of D. For example, the set of points interior to a simple closed contour. The next definition, multiply connected domain. A domain which is not simply connected is called multiply connected domain. Based on this definition, now we are going to prove a theorem. If a function f is analytic throughout a simply connected domain, then integral over C f of z dz equal to 0 for every closed curve lying in the domain D. So what is given? An analytic function is given. That function inside the simply connected domain. What we going to prove? The integral over C f of z dz equal to 0 where C is closed contour. So now we are going to prove, suppose if the C is simple closed contour, then by Cauchy theorem, integral over C f of z dz equal to 0. What is Cauchy theorem? If f is an analytic function and each C is a simple closed contour inside the domain D, then integral over C f of z dz equal to 0. Suppose if C is closed contour means that intersect itself a finite number of times. As shown in the below figure, you may take like that in the complex plane or xy plane, x axis, y axis, you may take the closed contour as like. So which is a closed contour C. Now the C can be divided into C1, C2, C3 and C4. Clearly that each Ci, that is C1, C2, C3 and C4 are simple closed contour. So therefore, once again by Cauchy theorem is true for each Ci. Therefore, we have integral over Ci f of z dz equal to 0. So that is integral over C1 f of z dz equal to 0 and integral over C2 f of z dz equal to 0 and so on. So therefore, we may write that integral over C f of z dz equal to summation I from 1 to n integral over Ci f of z dz equal to 0. So therefore, the theorem is proved. So for any f is analytic throughout a simply connected domain D, then integral over C f of z dz equal to 0 where every C is a closed contour. Next theorem, Cauchy integral formula. So let f be an analytic function everywhere inside and on a simple closed contour taken in the positive sense if z0 is any point interior to C, then we may write f of z0 equal to 1 by 2 pi I integral over C f of z dz divided by z minus z0. What is given? What we going to prove? So what is given? If f is an analytic function, where it is analytic? Inside the simple closed contour. We know simple closed contour means there is no multiple points. What does mean by positive sense? Positive sense means we are in clockwise direction. So that is given like that. So let us consider a simple closed contour C. So in a clockwise direction we can take like that. So within the point is going to be true, and each point, if z0 is any point interior to C, then you may write this expression. So now the function f of z divided by z minus z0. By convenient, we may take the function f of z divided by z minus z0, and it is analytic everywhere except at the point z0, since z minus z0 in the denominator. So omit the point f of z0 by drawing another one simple closed contour C rho, that is a circle with radius rho, and that C rho does not overlap to the original simple closed contour C rho. So now the function f of z divided by z minus z0 is analytic in the annular region bounded by C and C rho. So that is we have a circle C, and C rho be the another simple closed contour, both in the positive sense. So now we are considering the function in between the annular region. So by the principle of deformation of path, you may write integral over C f of z divided by z minus z0 into dz equal to integral over C rho f of z divided by z minus z0 into dz. So in the right hand side value, now I add and subtract with the f of z0. So therefore integral over C rho f of z minus f of z0 plus f of z0 divided by z minus z0 into dz. Now RHS can be split into two parts. The first one is integral over C f of z minus f of z0 divided by z minus z0 into dz, and the second point integral over C rho f of z0 divided by z minus z0 into dz. Now let us take equation number 1, and we are taking C rho be the circle with radius rho. Therefore we may write mod z minus z0 equal to rho, and which implies that z minus z0 equal to rho into e power I theta, and which implies we may differentiate the dz equal to I rho e power I theta into d theta. So now we substitute this value in the above equation. So therefore we may write integral over C rho f of z naught divided by z minus z naught into dz equal to, and the theta is the only variable and theta is varies from 0 to 2 pi. Since C rho is circle, so therefore the variation from 0 to 360. So therefore we may write 0 to 2 pi as a limit. F of z naught we keep as it is. We substitute z minus z naught as rho into e power I theta and dz value. So rho into e power I theta, rho into e power I theta get cancelled. I is a constant, f of z naught is a constant. So therefore we take outside. So I into f of z naught, then integral over 0 to 2 pi into d theta. The integral over 0 to 2 pi into d theta as theta, and limit is from 0 to 2 pi. So now we have substitute this limit. The upper limit is 2 pi, the lower limit is 0. So once again we can get 2 pi. So therefore we may write 2 pi I into f of z naught. So now we substitute this value in the equation 1. So therefore equation 1 implies integral over c f of z divided by z minus z naught into dz equal to integral over c rho f of z minus f of z naught divided by z minus z naught into dz plus 2 pi I into f of z naught. Now we move this step into LHS. So therefore minus 2 pi I into f of z naught equal to integral over c rho f of z minus f of z naught divided by z minus z naught into dz. So let us consider this equation number 2. So now we are going to evaluate RHS value. Since our hypothesis f of z is analytic within C rho, so by the definition of continuous, you may write for epsilon greater than 0, there exists some delta greater than 0, such that you may write the mod f of z minus f of z naught is less than epsilon, and whenever the modulus of z minus z naught is less than delta only. So therefore equation 2 implies we are taking modulus on both sides. So therefore we can write the modulus of integral over c f of z divided by z minus z naught into dz minus 2 pi I into f of z naught equal to modulus of integral over c rho f of z minus f of z naught divided by z minus z naught into dz, and which is strictly less than or equal to the integral over c rho the modulus of f of z minus f of z naught divided by modulus of z minus z naught into modulus dz. So modulus f of z minus f of z naught value is, we know, epsilon, and z minus z naught value is rho. So therefore which is less than epsilon by rho, and integral over mod dz. So the integral over the mod dz it should be equal to 2 pi into radius. So therefore 2 pi into rho. So therefore we are substitute. So the rho get cancelled. So once again we can get 2 pi epsilon. So now we substitute all the values in this, once again the equation 2. So the integral over modulus value should less than 2 pi epsilon, and which is equal to 0 as epsilon tends to 0, because epsilon is arbitrarily very small value. Therefore integral over c f of z divided by z minus z naught into dz equal to 2 pi I into f of z naught. So from this equation we need f of z naught alone. So therefore f of z naught equal to 1 by 2 pi I integral over c f of z divided by z minus z naught into dz. Cauchy integral formula is proved. Thank you.